For the next three questions, we're going to deal with angular momentum on a more terrestrial basis here with a tether ball. So here we have a vertical support rod is fixed at the center of a platform. A light string of length L is attached to the top of the support rod, and the other end of the string is attached to a sphere of mass M. The planet rotates with an angular speed that can be varied. When the platform rotates with a constant angular speed, omega makes an angle theta with the rod. The string makes an angle theta with the rod. So, part A says the platform rotates with a constant angular speed. Which of the above graphs correctly shows the magnitude of the angular momentum of the platform as a function of time? And so, with the platform rotating at a constant angular speed, that means that the angular acceleration is zero. There's no net torque, which means our angular momentum is constant. So the answer for part A is graph B, right? It shows a constant, non-zero value for angular momentum. So in addition, we have our formula that angular momentum is equal to the moment of inertia times the angular speeds. And if this is staying the same and the angular momentum of the system is staying the same, then the angular momentum is constant. So that is part A. Part B says the platform rotates with a constant angular speed. Is the net torque exerted on the platform about its center, clockwise, counterclockwise, or zero? And like we touched on in the last problem, if omega is constant, then alpha is zero. And we know that torque is equal to I alpha. So if alpha is zero, the net torque is equal to zero. So 1 point for saying that the net torque is equal to zero, 1 point for relating omega to alpha, which by saying if omega is constant, then alpha is zero, and 1 point for relating tau to alpha through the rotational inertia. That's part B, 3 points there. Part C says as the period of rotation becomes very small, what value does theta approach? And we're not allowed to use any formulas, and we don't really have any formulas, but we got to justify our answer here. So we say that as the period becomes small, that means that the platform is rotating faster. So it's really saying as the platform rotates faster, what happens? Well, it turns out that theta is going to approach 90 degrees. It's never going to get to 90 degrees, and we'll talk about why later. But you can argue that when the period is very, very large or infinite, that is, the platform's not moving, then theta is zero, right? If we're spinning the platform, then theta is not zero. So you can reason that as the speed increases, the angle increases. So we get a point there for relating the period to the speed, for saying that if the period is getting smaller, that means the speed is getting faster. And then you get a point for saying that the faster you spin, the larger that angle is going to be. So that's part C. So for part D, we found this formula, or a student derived this formula, and we need to discuss whether it's consistent with what we said in part C. And what we said in part C is that when the period goes down, theta increases. So let's see if that works for this equation here. So if the period decreases, that must mean that cosine theta must decrease, because G is going to stay the same, 4 pi and L are all going to stay the same. So is that true? As T decreases, does cosine theta decrease? Well, in order for the cosine of an angle to decrease, remember cosine is the x portion here, and as this angle gets bigger, right, the x component gets smaller. So that is true. When the period decreases and the cosine decreases, that means that theta is, increasing. So check. It does check out. So we get 1 point for addressing the functional dependence, that by saying, all right, if period decreases, then the cosine decreases. 1 point for getting the correct functional dependence, and then 1 for reasoning that, yes, as cosine theta decreases, theta does increase. And we are only talking about the first quadrant here. So 3 points for part D. So for part E, the students want to do an experiment to find acceleration due to gravity. And that's a perfectly reasonable way to do this. So what would we measure and how would we graph it? So we say here, a group of students changes L and adjusts T to keep theta constant. So theta's being constant, we're adjusting this, we're adjusting this. What could we do to get a straight line to find gravity? So what you could do, since you have T squared equals 4 pi squared cosine theta over G times L, okay, you want to put T on one axis and L on the other, all right? Now, or I shouldn't say it that way. We're going to graph T squared versus L. So something regarding T on one axis, something regarding L on the other axis, because what you could do is you could say T squared versus L, or you could say T versus the square root of L. It doesn't matter, okay? But you can't do T versus L because that's not going to be linear, and you can't do any other permutation. You've got to have the power relationships correct. And then, again, they don't ask you, but this whole thing here, if you do T squared over L, that's going to be your slope. Okay, everything else is constant, and you could solve for G. Again, they don't ask you to do that. They just ask, what could you do? So 3 points for this. 1 point for putting some permutation of T on one axis and some permutation of L on the other axis, and then 1 point for any correct power relationship, and it's really just these two. T squared versus L or T versus rad L. I guess you could do something weirdly different from that. I don't know why you'd want to. So that's part E. And then in a rare move, part F actually got a little bit easier. It says as the angular speed of the platform increases, so that's our omega, does the period of revolution increase, decrease, or remain the same? So since we know that we've used this a few times, velocity equals 2 pi r over t, and we know that the velocity is equal to omega times r, then we know that omega is equal to 2 pi over t. And you might have actually written that down without writing through all this. Sometimes I have to go through the whole thing to get there, but the angular speed is 2 pi over t. So if the angular speed is going to increase, how am I going to make this fraction bigger? Well, I got to make this fraction bigger by making the denominator smaller. So as omega increases, the period decreases. So 2 points for that. 1 for saying that t decreases, and then 1 point for realizing the relationship between omega and t. So that's it for 8-4.